let's just kind of set the stage here. So suppose we have a finite sequence. Okay, so a finite sequence now, it's going to be a sequence with just finitely many terms. So it'll be like A1, A sub 2, A sub 3, dot, 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 up to A sub n. Okay, so this sequence actually has an ending to it. Okay, the final term here is A sub n. Okay. Okay, and from this we're going to get the following definition. So DEF for definition. The sum A1 plus A2 plus A3 plus dot, 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 all the way up to A sub n. So this is quite literally adding together every term in the finite sequence. Okay, so I'm taking all these sequence terms and I'm adding them together. And this has a name. The sum is called a series. Okay. All right. A sub n. So A sub n, Saeed, that's the nth term of the sequence. Okay, so this is going to be the end. This is going to be the last term in this case. All right, so that's the definition. You take a sequence, in this case it's going to be finite, you add together every term in the sequence, and it has a name, it's called a series. Okay, so just very quickly, in other words, a series is the sum of the terms. Is the sum of the terms of a sequence. Okay. All right, so here's a very quick example, okay? So let's just consider the sequence 2, 4, 6, 8, 10. Okay, this is a finite sequence, and the sum 2 plus 4 plus 6 plus 8 plus 10 is a series. Okay, so I hope everyone sees the connection from the sequence to the sum. The sum here is simply just adding together every term in the sequence. So I took everything in the sequence, 2, 4, 6, 8, 10, and I've added it together. And this is an example of a series. Okay, so we're really just talking about series, we're talking about finite series, which is just, you take the sum of a finite sequence. That's what we'll do here in pre-calc, but it's in calculus 2 where you'll extend this notion to infinite sequences. And we're going to talk about that at the end of class very quickly. Okay? All right, good. So I hope everything's okay so far. So the next thing we'll talk about is something called summation notation. So we have a nice piece, we have a nice symbol to notate a sum. All right, so that's going to come next. So I'm going to go to a new page. All right, so this heading is called summation notation. Okay, and I also just need to put in parentheses, it's also called sigma notation. That's another name for this. Okay, so what is this? So this is so important. So this summation notation is used all across mathematics, upper level, lower level math, everywhere. So this is pretty important. All right, so just very quickly, a quick description. We have a convenient notation to represent a series. Okay, and here it is. Here's what it looks like. So you draw a capital sigma. I'm going to explain everything. On the bottom, you write k equals 1. On the top, you write n. Next to it, you write a sub k. Okay, and this is equal to, by definition, this symbol with everything here, it's just quite literally a1 plus a2 plus a3 plus ... plus a sub n. So that's what this symbol on the left stands for. You sum up this sequence a sub k, you start at 1, and the top number n tells you where you stop your sum. So since the top number here is n, I stop, my last term in the sum is a sub n.
So whatever number is in the last term, that's denoted as a sub n.
Right. So
in the series, I mean.
Yes. So if there was a 5 up here,
Mm-hmm.
you would just do a1 plus a2 plus a3 plus a4 plus a5. Then you'd be done.
Got it.
This tells you where to cut off your sum. Okay. So this is just yeah.
Good question. So the summation is the series. It's the same thing.
Yes. Yes. A summation. Yes, it's the same thing. Yeah. And just like this thing right here is called summation notation. Okay, so that's that. So just a quick piece of terminology. So let me just tell you guys what we call everything here. Okay, so this symbol, so that guy is the Greek letter capital sigma. Okay, so that's what that is. And also now these numbers on the bottom and top of sigma, they also have names as well. So K is called it's called the index of summation. One is the lower limit of summation. Okay, so that's this bottom number here, 1. And n is the upper limit of summation. Upper limit of summation. All right. So I just need to attach just some language to these symbols here just so I can speak about it and you guys know what I'm talking about. All right. So L is the lower limit of summation, N is the upper limit of summation. I mean, 1 is the lower limit of summation, N is the upper limit of summation. So here N is going to be just some positive whole number like 2, 3, 4, 5, 6. And it tells you when to cut off your sum. All right, so we're going to do some examples. Okay, so example. Let's talk about this guy. So we have the sum from k equals 1 to 5 of 2k. All right, so what is this equal to? Well, I ought to plug in the numbers 1 through 5 into 2k and add them together. All right, so it looks like this. So it's going to be 2 times 1. You plug in the lower limit of summation, and you keep going until you hit the upper limit of summation. So it's 2 times 1 plus 2 times 2 plus 2 times 3 plus 2 times 4. And since this upper number is 5, I stop after plugging in 5. Okay?
Is k the number of the first term in the sequence, or?
K is telling you where you need to plug in your index, where you need to plug in the numbers 1 through 5. So I have this expression here, 2k. I need to plug the numbers 1 through 5 in for k.
Okay.
See that? I plugged in 1, 2, 3, 4, and 5 in for k.
Yeah.
All right, so that's what this is, and now you can simplify this. So this is 2 plus 4 plus 6 plus 8 plus 10, and this is 30. Okay, so the value of the sum. So the way you would kind of say this out loud, you say the sum of 2k from k equals 1 to 5. That's one way to say it. Or the sum from k equals 1 to 5 of 2k. You can say it like that too.
So basically, it's just another way to write out the sequence, but an expanded form. I mean, sort of.
Right. So you're not writing the sequence though. You're summing them. You're summing the sequence. You're adding it together. A sequence is just the list of numbers. The series is adding up that list of numbers. So it does have a different meaning. All right, so now I just have an image which just kind of summarizes everything so far that we did. Let's just take a look at this quickly. Okay, so basically it's everything I wrote, but just in one image. So k is the index of summation, 1 is the lower limit, 5 is the upper limit, and the expression that appears next to the summation symbol, next to sigma, that's the explicit formula for the kth term. Okay. And again, this means you're just adding up the sequence when you plug in the numbers from 1 to 5. You plug them into k. All right. Okay, so far, the lower limit of summation has been 1. It doesn't need to be 1, so we can change that. So the lower limit of summation doesn't have to be 1. Okay, as this example will demonstrate. So how about this guy? You have the sum from k equals 2 to 4 of the sequence 3k minus 1. Okay, what will this equal? Okay, so this notation here, it tells me I need to plug in 2 into this guy, then I need to add together plugging in 3 into this guy, and add in plugging in 4 into this guy. And then you stop. You stop at this top number here. So this will be, I'm going to plug in 2 first. It's 3 times 2 minus 1 plus 3 times 3 minus 1 plus, so I just went down because I ran out of room on the right side, 3 times 4 minus 1. Okay, and you stop at 4 because that's the upper limit of summation. All right, so it's this top number that's going to tell you where to stop adding terms. Okay, so I hope everyone sees what I did. I plugged in 2, I added together plugging in 3, and added together plugging in 4. And I'm plugging these values in for k. Okay.
So the upper and lower just are a way to indicate how many terms you're plugging in, though, right? How many terms are in this series?
Sure. Or alternatively, it tells you where to start and stop your sum. You start it at plugging in k equals 2, as I did right here, and you stop at plugging in k equals 4. Right? And now you can just simplify each of these parentheses. So the first one is 5 plus, the next one is 3 times 3 minus 1, which is 8. And the last one is 4 times 3 minus 1, which is 11. And this is 24. All right. So very important, very fundamental. So I hope everyone kind of sees like the definition of this notation, okay, and how it works. And it's very powerful because it can be quite like cumbersome and annoying to write this out. And it's but to write out the sum in expanded form, but you can write it very compactly and in a very short way, just with the summation symbol. All right. So it is very useful. Okay. Good, good, good. All right, so let's kind of move on. So I need to talk about something called partial sums. Okay, partial sums. Okay, so let's give a definition here. So let A1, A2, A3, dot, dot, dot. So this is now going to be an infinite sequence, okay? So let this guy be an infinite sequence, okay? So here is the definition. The sum of the first n terms of the sequence is called the nth partial sum and is denoted by capital S subscript n. So you have an infinite sequence now. And suppose you just want to take the sum of the first n terms. So it's still a finite sequence. So like, for instance, I have this infinite sequence. I want to take the sum of the first 5 terms. Well, the name of that is just called the fifth partial sum. Okay? So now let's notate this using our previously learned summation notation. So using summation notation, S sub n is defined to be, you take the sum of the first n terms. So you write down your sigma. It goes from k equals 1 to n, because you want to take the sum of the first n terms, a sub k. All right. And then if you expand this out, of course, using the definition of summation notation, this is just a1 plus a2 plus dot, 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 up to a sub n. Okay, so the nth partial sum of the sequence, it's just the sum of the first n terms. And you can see that right here. I've just summed up the first n terms of a sequence. Difference here is that the sequence is infinite. Okay. All right, good. So now let's talk about sums of arithmetic sequences. Yeah. So that'll be next. Okay, good. So here we go. So we actually just get an explicit formula for the sum of an arithmetic sequence, and that's going to come in the form of a theorem. Okay, so theorem. All right, so let A1, A2, A3, dot, 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 be an arithmetic sequence. Okay. Now, let me just remind you what an arithmetic sequence is. It means that the difference between any two consecutive terms is the same, no matter which two terms I pick. So A3 minus A2 will be the same as A2 minus A1, and it will be the same as A4 minus A3, and so on. So you take two consecutive terms, subtract them, it's going to be the same no matter which two consecutive terms you pick. That's an arithmetic sequence. Okay, so we have a formula for the nth partial sum, a very nice formula. Then the nth partial sum has the formula. So that's a very pleasant formula. So S sub n, the nth partial sum, which in other words is the sum of the first n terms, is simply given by this. It's n times a1 plus a sub n divided by 2. Okay, so that's really nice. You can sum up the first n terms of an arithmetic sequence very quickly just by plugging into a formula. So I'm not going to present the proof of this theorem. It's a little bit outside the scope of this class, but if you're interested, I can show it to you at another time. Okay? So they're going to do an example. All right, so we're going to see how powerful really this theorem is. Okay, so here we go. Find the sum of the first. Find the sum of the first 20 terms of the sequence. So here's a sequence. It's 1, 5, 9, 13, 17, and so on. Okay, so I have given you an infinite arithmetic sequence, and I want you to find the sum of the first 20 terms, okay? So I don't want you to just list out the first 20 terms and add them together using a calculator or something, because that's not very efficient. We have a much more efficient way of doing this by using the formula, okay? So we use the formula. So let's just call upon what we need for the formula. We need n, we need a sub 1, and we need a sub n. Okay, so n here is 20. We want to find the sum of the first 20 terms, okay? So so n is 20. A sub 1 is just the first term of the sequence, which is 1 in this case. Now a sub n, we need to actually find the 20th term of the sequence. We need to find a sub 20. Okay, so that's maybe like the trickiest thing. So we need to find a sub 20. Now, if you remember, we do have an explicit formula for the nth term of an arithmetic sequence. So a sub 20 is going to be a1 plus 19 times the common difference d. Okay, so that comes from the formula for the nth term of an arithmetic sequence. Good, and we can actually fill in this information immediately. So a1 we have already, it's 1, plus 19 times d. Now, what's d here? It's the common difference. It's the difference between any two consecutive sequence terms. So 17 minus 13 is what? That's 4. 13 minus 9, also 4. 9 minus 5 is 4. 5 minus 1 is 4. So that tells us that the common difference is 4. Good. And what does this come out to? Yeah, so work this out. You get that 1 plus 19 times 4 is 77. Okay, so we have all the pieces of information we need. So Sn is, I'm going to rewrite the formula. It's n times a1 plus an over 2. So we want S sub 20. So we have to plug in. So n is 20, so I plug that in right here. A1 is 1. A sub 20 is 77. And then you divide by 2. All right, and you just work this out. You will see that this becomes 10 times 78, which is 780.
Why is a sub n going to be 77 again?
Okay, so we have for an arithmetic sequence, we derive the formula for the nth term. A sub n is given by the initial term plus n minus 1 times the common difference d. That was from last class when we derived it. So I just applied this formula in the case of n equaling 20. And that was right here. Okay.
Got it.
D was 4, plugged it in, got 77. That was maybe like the trickiest part of this, was just finding that 20th term. All right, so you can kind of see the value of this formula. I was able to sum together 20 numbers pretty quickly. So as opposed to doing it manually, as opposed to literally listing out the first 20 terms of the sequence and using a calculator and adding them together, I was able to find out immediately that the sum of the first 20 terms was 780. And you can see how valuable this formula would be. If I told you to find the sum of the first 1,000 terms, you could find it very quickly, way quicker than using a calculator. Right, so this is definitely useful, and on the homework you'll have some practice with this. Okay. All right, so good. So we're going to now move on to sums of geometric sequences. Okay, unless anybody has any questions. Okay. Good. So let's now do sums of geometric sequences. So we just did arithmetic sequences. We took their sums. Now let's take a geometric sequence, take their sums. Let's see what happens here. Okay. So sums of geometric. Okay, so this is very beautiful. So theorem. Okay, so let A1, A2, A3, and so on be a geometric sequence with common ratio R. Okay, so let me just remind you that a geometric sequence, it means if I divide any two consecutive sequence terms, I'll get R no matter what. So A3 divided by A2 will be R. A2 divided by A1 will also be R. A7 divided by A6 will also be the same number R, and so on. That's a geometric sequence. That's the definition. Okay, so suppose we have such a sequence with common ratio R. then we have an amazing formula for the nth partial sum of this sequence. So then Sn, which is the sum of the first n terms of the sequence, it's given by this. A sub 1, the initial term, times 1 minus r to the nth power divided by 1 minus r. Okay, so let me just remind you what this S sub n means. S sub n is just shorthand for the sum of the first n terms of this sequence, okay? So S sub 100 would be A1 plus A2 plus A3 plus and so on up to plus A sub 100. All right, so we have a really nice formula for such a sum. Okay, so I'm actually going to give you guys the proof of this. Don't worry about replicating the proof or understanding it completely. Maybe just sit back and try and enjoy it. It's kind of nice. So let me just start this off. So here's the proof. Here's the proof. Okay, so firstly, we want to recall that we have a formula for the nth term of a geometric sequence. So recall that the nth term of a geometric sequence is given by, so this was by last class. If I give you a geometric sequence, you can get the nth term by doing the initial term multiplied by the ratio to the n minus 1 power. Okay, so this was last class. Okay, good. So then the nth partial sum is given by, so by definition, the nth partial sum is just the sum of the first n terms, okay? So I'm going to use this formula now and sum together the first n terms. So it's a sub 1 times r to the 0th power, which is just 1, so it's a sub 1 itself, plus a sub 2 times r to the first power, yep. No, sorry, it's always a sub 1. Yeah, it's always a sub 1. The only thing that changes is the power of r. It's a sub 1 plus a sub 1 r plus a sub 1 r squared plus dot, 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 up to the nth term. The nth term is a sub 1 times r to the n minus 1. Okay, so I just wrote out the nth partial sum of the sequence, but using now the explicit formula for each term, okay? Okay, good. So what you can do here is you can factor an A1 from the right side. You can factor out an A1 from the right side here, okay? So now factor an A sub 1 out from the right side. Okay, so what does that give us? So the left side stays exactly the same. And if I just factor out an A1, what's left? Well, what you're left with, you have 1 plus r squared plus dot, dot, dot plus r to the n minus 1. Okay, because all of these guys up here, they have an A1 attached to them. So I'm just going to factor it out, and what you're left with are just these powers of r. Okay, so I'm going to call this equation 1. So now this is where you kind of have to be a little creative, and maybe you wouldn't know to do this step, but luckily people smarter than me have figured this out already. So the next step you want to do is you want to multiply both sides of 1, of the equation right above, of equation 1, by 1 minus r. Okay, so I take equation 1 right here, and I multiply both sides of it by 1 minus r. Okay, so what does that look like? Well, the left side, you have 1 minus r times Sn. And on the right side, you have a sub 1 times 1 minus r. And then plus 1 plus r squared plus dot, 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 plus r to the n minus 1. Okay, so just multiply both sides of this guy by 1 minus r. Okay, good. So what we want to do next is you want to actually multiply out this right here. Okay. So this highlighted part, it's two polynomials. You can multiply them together as if they're two polynomials in the variable r. So this will be a sub 1, open up parentheses. So if I distribute a 1 to every guy here, it stays the same, right? You're just going to get itself. So that's distributing the 1 through. So that's 1 plus r squared plus dot, 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 plus r to the n minus 1. Now you need to multiply through this minus r. So you do minus, open up a parenthesis. So if you distribute an r into each of these guys, this 1 becomes an r, the r becomes an r squared, plus dot, 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 and the r to the n minus 1, when that gets multiplied by r, it becomes r to the n. Okay, so I know it looks a little sloppy over here because I'm running out of room. All right, anyways, so now look at this. You get some really nice cancellations. You see here that this r is going to cancel with that r because of the minus sign. You have r minus r. Similarly, r squared is going to cancel with that r squared. And the r to the third is going to cancel with an r to the third here. And r to the n minus 1 is going to cancel with an r to the n minus 1. The only surviving terms here is 1 and minus r to the n. 1 minus r to the n. And this is by cancellations. A lot of cancellations happen. Okay. All right, so we are pretty much done here. So look at what we have so far. We have that 1 minus r times Sn is equal to that. So let's just summarize. Thus, 1 minus r times Sn is equal to a1 times 1 minus r to the n. And now just isolate this for Sn, because that's what we wanted in the first place. We wanted a formula for the nth partial sum. So divide both sides by 1 minus r, and you get a sub 1 times 1 minus r to the n divided by 1 minus r. Okay, so I divided both sides of this equation by 1 minus r to isolate Sn. And there you have it. That's the proof. And that's exactly what the theorem stated. Okay. So a very nice, very important formula. So any questions? Don't worry about this proof. I thought it would just be something nice to show everyone. All right, good. So let's do an example problem using this formula. Then I'll just say a quick word about infinite series, and then we'll be done. Okay, so example. Find the 11th partial sum of the series. Okay, so I'm not going to write it in summation notation. I'm just going to write it out of the sum of the series. 8 plus 4 plus 2 plus 1 plus dot, dot, dot. Okay, so this is a series And I want you to find the 11th partial sum, aka the sum of the first 11 terms of this guy. Okay. All right, good. So for the formula, we need a sub 1 and the ratio r. So let's list that out. We need a sub 1 and r. Okay, so firstly, a sub 1 is just the first term, so it's just 8. That's going to be a sub 1. So we have that. R, so R is given by dividing a sequence term by its previous sequence term. Okay, so you can do 2 divided by 4, or 4 divided by 8, or 1 divided by 2. You'll see that in any case, the ratio is 1/2. Okay, so you can just do 4 divided by 8, which is 1/2. All right, so we have everything we need. All right, good. So thus, S11, S sub 11, the 11th partial sum. So the formula is A1 times 1 minus r to the n over 1 minus r. So it's going to be A1, which is 8, times 1 minus the ratio, which is 1/2 to the 11th power, divided by 1 minus the ratio, 1 minus 1/2. Okay. Very cool. And now you can just simplify this. Okay. So you'll just see that this is 8 times 1 minus. So 1 over 2 to the 11th power, that's actually 1 over 2048. Okay. And if you simplify the 1 minus 1/2 down here, that's just 1/2 itself. All right, so I'm just doing some simplification. Okay, good. So this will come out to 16 times 2047 over 2048. And this is 2047 over 128, which is approximately, so now I don't have an exact, so this is a rational number, but just it has a lot of decimals, but approximately it's 15.99. Okay. So how cool is that? That's the sum of the first 11 terms in this series that we just got with the formula. So it's a lot quicker than actually doing the math and doing it manually and adding together the first 11 terms. All right, so these sequences are very important. I mean, these formulas for the series are very important. All right. So any questions about anything I did here, or yeah, so any questions at all? Okay. All right. So that will finish that up. Now I'm just going to say a quick word about infinite series. Okay. So this is like if you're going to take Calculus 2 in the future, you're going to be talking about taking infinite sums. Okay. So how can we kind of sum together an infinite sequence? So let me just talk about that. So a quick word about infinite series. Okay, cool. So this is kind of interesting. So so basically, like in Calculus 2, you're going to be given an infinite sequence, A1, A2, A3, A4, and so on forever. Okay, it's an infinite sequence. Okay, now you're going to want to kind of discuss this thing here, the sum from k equals 1, not to n now, but to infinity. So you replace that upper limit of summation with an infinity symbol. It's not n anymore. So this is in a sub k. So this is intuitively supposed to represent an infinite sum of numbers. So a1 plus a2 plus a3 plus a4 plus forever. Okay, so you're adding things. You're adding an infinite amount of numbers, okay? So in some cases, this is going to shoot off to infinity, in which case there's no meaningful way to assign a number to this sum. But in some cases, it will actually settle down to a finite number. And that's a very pleasant thing, and it's really nice. So how do you actually define this thing? So basically, you look at the partial sums. Look at the partial sums. So we need to actually give like a definition for what it means to sum together an infinite number of numbers. Okay. So basically, so given an infinite series, k equals 1 to infinity, a sub k, you look at the partial sums, S sub n, okay? So you look at the sum of the first term, the sum of the first two terms, the sum of the first three terms, and so on. And these partial sums, they actually form a sequence themselves, okay? So they form a sequence. Okay, so the sequence looks like this. It's S1, S2, S3, S4, and so on. It's an infinite sequence, okay? And it's given by taking this, it's given by chopping this sum off to a finite number. So S1 is just going to be the sum of the first term. S2 is going to be the sum of the first two terms. S3 here is going to be the sum of the first three terms, and so on. And this gives you a legitimate infinite sequence. Okay, you can see that this is going to be a number, that's going to be a number, and so on. So basically, if the sequence S sub n, the sequence of partial sums, settles down to a finite number, so if the sequence kind of, it settles down, doesn't shoot off to infinity or have any crazy kind of behavior, then this thing, this infinite sum, k equals 1 to infinity, is meaningful. And the value that you assign this infinite sum is the value that this sequence of partial sums settles down to. So you take a limit of the sequence of partial sums. Okay, so that's more or less the definition of how to sum an infinite amount of numbers. You look at the sequence of partial sums and look at the behavior of that guy. All right, so here's a very interesting example. It turns out that if you take this infinite sum, so you do k equals 1 to infinity of 1 over k squared. Okay, so what does this look like if you write out a few terms? It's 1 plus 1/4 plus 1/9 plus 1 over 16, and so on. This actually settles down, amazingly enough, the value of this infinite series, it comes out to pi squared over 6. Okay, and what's crazy about this is that, you know, pi has to do with geometry and circles mainly, and it looks like this sum really doesn't have anything to do with circles or geometry. But yeah, it turns out you take this infinite sum, 1 over k squared, it settles down precisely to the value pi squared over 6. All right, and this was a very famous mathematician named Euler first showed this. So this was due to Euler.